This paper deals with the notion of fairness in machine learning. The context is a classifier. We want to learn a boolean function which has arguments which are either non-protected or protected. Examples of protected features would be, for example, gender or race. And the idea is we want to learn a function, a classifier, which does not depend on gender or race or other protected features. One concrete example is whether a bank should approve a loan to a customer. We would hope that the model we learn would not take into account gender or race of the client. Before trying to construct a fair model from data, we have to ask certain questions like, what is a criterion for dataset bias, for fairness of a model, or fairness of a particular decision? And then we'll be able to go on to describe how to learn a fair model from possibly biased data. Now, the criterion, which is fairly obvious to decide whether a model is fair or not, is that it is only a function of the non-protected features. So this is called fairness through unawareness. Now we can detect unfairness by exhibiting two examples. For example, Alice and Bob, who are identical in terms of salary, age, etc., with unprotected features, but differ obviously in gender. Alice is refused a loan, but Bob isn't. So we're actually primarily interested in learning fair models from a possibly biased data set. So in our experimental trials, we used a SAT solver. So the model we're trying to learn is a KDNF, where K is some small constant, which matches as much as possible the data and is 100% fair. And we coded this problem of finding the KDNF as a SAT instance. So the main principle is we impose fairness, and this is necessarily at the cost of accuracy in the case of biased data. We may further sacrifice accuracy in order to obtain a simple model, for example, a KDNF with K small. What I haven't talked about here is the local notion of fairness, the fairness of a particular decision. Now here we actually found two different notions, and we analyze the complexity, computational complexity, and here complexity may be an issue. But the main positive point of this paper is that we've shown that it is possible to learn a fair model from possibly biased data. Nonetheless, there is obviously further work required to deal with, for example, correlations between protected and non-protected features, or presence of irrelevant features which can hide dataset bias. So now we'll look in detail in the notion of fairness in machine learning. So we're interested in defining criteria for fairness of a model, dataset bias, and fairness of a particular decision. And in particular, we want to know how to learn a fair model from biased data. So we want to learn a classifier which is only a function of the non-protected features. And this criteria is called FTU, fairness through unawareness, that the model should only be a function of the non-protected features. We can detect unfairness by exhibiting two examples. For example, Alice and Bob, who are identical in the non-protected features but differ only in gender. And for example, Alice is refused a loan, but Bob isn't. Now, this seems like an obvious criterion, but we can nevertheless criticize it. So one objection is that there may be correlations between protected and non-protected features. in a very extreme example, the bank can say it's not unfair to women, they just don't give loans to people who are pregnant. Okay, this is a bit extreme, but you can imagine other examples where the bank decides to give loans to computer programmers but not to nurses. There is clearly correlation between jobs and gender. So in this example, the bank would not be being very fair to women. Another minor point is that positive discrimination may be a good thing, so that applying blindly the FTU criterion is maybe not always what we want. For example, height restrictions for army recruits are less strict for women, which is we find completely normal. Now, we can also use FTU as a criterion for dataset bias by just looking for two examples which differ only in the protected features and have different outcomes. Now, this criterion can be tested in linear time. So that's good news. But we now have new objections to using FTU as a criterion for dataset bias. The difference between analyzing a dataset and analyzing a model is that a model is a total function, and a dataset is at best a partial function, and sometimes if there are contradictions in the dataset, it's not even a function. Now, a new objection is that bias can go undetected if there are irrelevant non-protected features. For example, to go back to our example of Alice and Bob, maybe the bank gave a loan to Bob and not to Alice because Bob is Sagittarius and Alice is Cancer, or because Bob has a different shoe size to Alice. Clearly this is very odd, and it means that we can't automatically detect bias by applying blindly FTU if there are lots of irrelevant features. Another more subtle point is that maybe just looking at pairs of examples is not the only criteria for deciding bias. Because there's a difference between bias and fairness and arbitrary decisions. Perhaps the decision to give Bob a loan and not Alice was just an arbitrary decision which had nothing to do with gender. This can happen, for example, we can see this if we have 4 people who are identical except for gender, Alice, Bob, Carol and Dan, and Alice and Dan have their loans refused, and Bob and Carol have their loans approved. So in this case, there's obviously arbitrary decisions, but is this model, is this data set biased or unbiased? Okay, but we looked at it from a theoretical point of view. The criterion for dataset bias has to satisfy certain axioms. We wrote down 5 axioms. 4 of them are completely uncontentious. 1 we could discuss. So simplicity, in red, is this 5th axiom, simplicity, that bias can be proved by exhibiting just 2 examples. For example, our Alice and Bob examples. We proved that just any criterion which satisfies these 5 axioms must be FTU. There is only 1 criterion. In fact, we went further to say that if we want to add an extra axiom that our criterion is invariant to the addition of irrelevant features such as month of birth or shoe size, then there is no criterion. So this shows that our notion of our axiom of simplicity is maybe not the right axiom. We could include different axioms and get different criteria. Anyway, testing the fairness of a data set is a relatively minor problem compared to the fairness of a model or the fairness of a particular decision. So let's now look at the fairness of a particular decision. Let's take a concrete example. Emma is an unemployed woman, and she wants to know if she was refused a loan because she is a woman. Now, suppose the bank uses the following simple model. It refuses a loan if a client is unemployed or if they are a woman. Now, clearly, this model is unfair with respect to gender. But the bank claims that the actual decision concerning Emma was not unfair because Emma is unemployed, and that's a reasonable reason for refusing a loan. Emma points out that there are actually two possible explanations for the loan refusal, one that she is unemployed and one that she is a woman, and hence the decision should be considered unfair. Now, who is right here? In fact, no one, or both. There are two possible definitions of fairness, depending on whether you say that we call this universal fairness or existential fairness. A decision is universally fair if all of its explanations are fair, existentially fair if at least one of its explanations is fair. So without going into the technical details, we saw with that concrete example that one explanation was that Emma was unemployed, one other explanation was that she was a woman. So Emma's loan refusal is existentially but not universally fair. Now, looking at the complexity of checking fairness. Now, fairness of a whole model is clearly a co-MP problem because a certificate of unfairness would be, for example, Alice and Bob, two examples as we've seen. So a certificate can be checked in polynomial time. So this puts us in co-MP, and depending on the type of model, it may be co-MP complete or not. Now, checking existential fairness, that's the bank's version. Although technically in co-MP, in fact, can be solved relatively quickly because we only need to do an exhaustive search over all combinations of our protected features. Now, if our protected features are gender, religion, race, there are not that many combinations, so the bank could easily try all combinations. However, checking universal fairness, that's the client's version, is in the second level of polynomial hierarchy, so it looks like we're going to really have to check all possible examples. So the computational complexity is very different between existential and universal fairness. Okay, what we're really interested in is learning a fair model from possibly biased data. So the underlying principle is we always impose fairness, possibly at the cost of accuracy. Indeed, if the dataset is biased, this must be at the cost of accuracy. The solution is fairly easy. It's a majority vote solution. If you have several examples in your dataset with the same non-protected features, with giving different possible outcomes, you just do a majority vote. This will maximize accuracy. We can further sacrifice accuracy in order to obtain a more simple model. So concretely in our experiments, we looked for a KDNF and we coded this as a SAT problem. If we make our KDNF only a function of the non-protected features, then our model is necessarily fair. So imposing fairness is a fairly simple thing to do. Then we have the choice of how many terms we want in our KDNF, for example, if that's what we're trying to find. Once we've fixed a constant, a small constant for the number of terms, then we can set up variables for our SAT instance. There'll be variables to say if a kth term contains a feature xj, another one to say if a kth term contains the negation of xj, another variable to say if the ith example satisfies the kth term. And then there are clauses in our SAT instance to impose constraints such as each positive example satisfies some term, no negative example satisfies any term, and then certain constraints to code the semantics of the variables. Now the size of our coding is n times m times k, where n is the number of examples, which can be large, m is the number of features, which is usually smaller, and k is our small constant, which is the number of terms in the DNF. So clearly, using a SAT solver is a solution for small or medium-sized problems, but not for very large problems. So in a particular example, in our experiments, we derived a simple model from the Compas dataset. This dataset is derived from the Compas algorithm used for scoring a criminal defendant's likelihood of reoffending. It includes many protective features concerning race or gender. In fact, the dataset is so biased that the maximum feasible accuracy is less than 70%. By sacrificing a bit more accuracy in order to obtain a simple interpretable model, we obtained the following model, which has a 66% accuracy and is completely fair. It's described in only five lines. Now we can see from this model that it is fair. It doesn't take into account any protected features such as race. So in conclusion, we've seen that FTU is the only criterion for dataset bias which satisfies our 5 axioms. However, the simplicity axiom is questionable, so there may be other criteria. We can test in linear time whether a dataset is biased using FTU. Now, the fairness of a decision is more complicated. There are at least 2 different notions of fairness of a decision, and complexity may be an issue, especially for checking the existential fairness of a decision. But most importantly, as a take-home message, I think that we need to emphasize that we've shown that it is possible to learn a fair model even from biased data. Okay.